Hi everyone, welcome back for the last set of lectures. So first of all, I'm going to talk about some of the newer features in OpenMP. So the OpenMP specification is now getting very big, rather unwieldy, and to keep track of everything that's in there. So this is really just a selection of some things that have been added relatively recently that you might possibly find useful or interesting. Okay, so kind of relatively recent history. It's really quite old now, if you like. OpenMP 4 came out in 2013, and that was when the first Accelerator offloading support went in. Also, support for thread affinity and additional stuff for tasks. 4.5 was mostly corrections and a few new features, and 4.5 is now pretty commonly available in production compilers, with the possible exception of the offloading features. Version 5 came out in 2018. Say a bunch of extra features, some extensions and reworking of some of the offloading stuff, the new memory model, and basically an upgrade to the base language version support. So the OpenMP now supports reasonably up-to-date versions of Fortran, C, C++, which it was previous up until version 5 was kind of lacking. And some implementations out there support the whole of 5.0. And then the most recent one is 5.1 from last year, which has even more features in it. But the implementation is still in production compilers, is still mostly work in progress. You won't find many 5.1 compliance compilers out there yet. So the ones I'm going to talk about here are user-defined reductions, construct cancellation, the SIMD directive extensions, a few more bits about tasking, and thread affinity stuff. And then I've got a whole separate talk about the accelerator offload things. Okay, so user-defined reductions. So up to version 3.1, you can't do reductions on things like objects or structures. The reduction clause only applies to variables of basic type, including arrays, but just arrays of basic types as well. So the user-defined reduction extensions in 4.0 added support for basically doing reductions on whatever you want. So the way this works is there's a declare reduction directive to define your own new reduction operators, and then you can use those in a reduction clause like you would normally do. So what this looks like is a declare reduction directive. So that takes you have to specify several things. You have to have the reduction identifier, which is the name or the symbol that you're going to use in the reduction clause, a list of types, and then a piece of code that specifies how to combine two things of those types together to form the reduction. And optionally also the identity expression to initialize the private copies of the types that you're going to use. Okay, so in a bit more detail, the reduction identifier gives a name to the operator. You can overload that for different types, and you can also redefine that in inner scopes. So the type name list is just a list of types, list of all the types to which it applies. And the combiner expression specifies how to combine values. And yeah, the identity is specify the identity value of the operator. So that's the thing that can be that's the value with the private copies will be initialized at the start of the whatever it is, the parallel region or loop directive, for example, that has the reduction clause on it. Okay, so here's a little example. So this is to do, so you can do merging of vectors in the standard C++ library. So I'm going to give the name to the operator called merge. Okay, and this applies to std vectors of type int. And then we have this little expression which says how to combine two things of this type. So there are these two special variables here, also pseudo variables, which are omp out and omp in. Okay, so it assumes that this is telling the compiler how to produce one value from two values. So the out is going to be the private copy that's going to hold the combined value, and omp in refers to the other private copy. Okay, so it assumes that this takes omp in and omp out, combines them together, and produces the result in omp out. Okay, so this one does what this one does is it says insert. Okay, insert in omp out at position omp out end the values from omp in begin to omp in end, from the beginning and end. Okay, so this basically adds the values tacks those onto the end of the vector omp out. So then I can just use merge as a reduction operator in a reduction clause with some list of vectors in the clause. So this basically allows you to define reductions for essentially whatever you like and however you want. Okay, any questions about that? Okay, the next one is construct cancellation. So this is designed to provide you with a clean way to signal early termination of an OpenMP construct. So the idea here is that you've got multiple threads doing some calculation inside a parallel region, for example, and you want to be able, one thread, to signal to all the others that actually, okay, we're done now. So stop whatever you're doing and jump to the end of the parallel region. So the idea is one thread raises a signal, and as soon as the other threads observe that signal, then they just stop what they're doing and jump to the end of the construct. So this just looks like OMP cancel. Okay, so this is Fortran syntax, same C++, hash pragma OMP cancel. Then you have to give the name of the construct that you're cancelling, and then there's a conditional expression. So if expression is true, then the cancellation will happen. So the cancel directive does the signaling, and that can be parallel sections, do or for, so work sharing loops, or task group construct. And then you also have a cancellation point directive. So this doesn't raise the signal, but this indicates a place at which threads. So that also happens in directives and also in places like barriers as well. But you can also code explicit points to say, okay, at this point, check to see if another thread has raised the cancellation signal. Okay, so a bit of sketchy code here, but the sort of use case might be, if you're doing some, if you have multiple threads searching for something, but you're only interested in the, once the first thread that finds something, then you're done. So you might have a parallel loop, and then you could say, okay, so each iteration of the loop calls some function and returns a logical value. And so the first thread that finds Eureka equals to true will raise the cancellation. And all the other threads, the next time they hit the cancel directive, they will stop executing the loop iterations and jump to the end of the parallel region. So next topic is the portable SIMD directives. So these are perhaps a slightly odd thing to find in the OpenMP standard, because really they are orthogonal to threaded parallelism. Okay? So this is to do with vectorization and SIMD instructions. But the rationale here was really, it was OpenMP was a convenient place or a convenient standard to standardize this stuff, but it does sit rather, it does look slightly odd in contrast to all the multi-threaded stuff which OpenMP is normally concerned with. So the rationale here is that many compilers support their own, or used to, and still do typically, support their own set of SIMD directives to aid the vectorization of loops. This is because the compiler can typically struggle to generate SIMD code without you providing some additional information about the code, about the loop. So OpenMP provides a standardized set of these, so which hopefully will be portable across all compilers. So the basic directive is the SIMD directive, to say that to indicate the loop should be SIMDized. Just looks like hash pragma OMP SIMD followed by a for loop, and that will execute the iterations of the following loop in SIMD chunks. So it basically tells the compiler to generate vectorized code for that loop. It doesn't divide the loop across threads. It just does the vectorization. So the terminology here, so a SIMD chunk is a set of iterations executed concurrently by SIMD lanes. And then the SIMD directive takes various clauses that control the data environment and how the loop is partitioned and so on. There's you can specify a safe length, so that's an upper bound on the number of iterations in a SIMD chunk. You can have a linear clause, so this lists variables with a linear relationship to the iteration space, so otherwise known as induction variables. So a variable that's incremented by a constant amount on every iteration, for example. because those things, the compiler will normally detect a dependency on those, because there is a formal dependency of each value, each loop iteration. The value in those variables has a dependency on the previous one, but you can, the compiler can transform that to avoid the dependency and permit. Don't specify the alignments, so this is very important for enabling this is one of the things that the compiler really needs to know but can't in general tell from inspecting the code, is how your data structures, how your arrays, for example, are aligned. So you can specify the alignments of variables so that the compiler knows and has a better chance of generating the vectorization. So clauses like private, last private, reduction, collapse basically have their usual meanings. There's also a declare SIMD directive which is able to generate SIMDized versions of functions. Okay, so provided provided the functions have the appropriate type signature and are side effect free, then it'll encourage the compiler to generate vectorized versions of functions. And then you can combine the SIMD directives also with the OpenMP loop constructs. So if you want to both parallelize the loop across threads and vectorize it within every thread. Any questions about that? That's kind of a very quick overview of the SIMD stuff. But if you've used the vectorization directives in another compiler, then the OpenMP ones are essentially very similar. They just provide a standardized way of doing it, so that you don't have to, if you change compiler, you don't have to add yet another set of vectorization directives. Okay, there's been also quite a few extensions to the tasking in OpenMP. I'm not going to cover them all, just to mention a couple of perhaps the more interesting ones. The first one is the task loop directive. So this provides a convenient way to turn loop iterations into tasks. So you can have a loop, and then you can put a #pragma OMP task loop directive on that, and you can then specify a grain size, for example. So in this example, what this will do is it'll take every group of 16 iterations and will package those iterations up as an OpenMP task. It's really just a convenience. I mean, you could fairly reasonably easily modify the code to do this, but it's slightly messy. So this is a syntactic convenience rather than anything really really new or semantically different. You can also, you can either specify the grain size, or you can specify the number of tasks. Okay, so how many tasks do you want the loop to be split up into? So you can do it either way. Another interesting one is task dependencies. So this is a way of allowing you to specify ordering constraints between tasks. So otherwise, unless we have some synchronization point, it's normal tasks are assumed to be all executable in parallel. But quite often that's not the case. You want to be able to specify some ordering constraints between tasks. So the way this works is there's a depend clause on the task construct. Well, this takes a type, so there's a type of dependency, and then a list of variables. And that list can contain subarrays. So OpenMP includes a series of arrays in C. So if the way this is specified is that, okay, if the depend type is in, then the generated task will be a dependent task of all previously generated sibling tasks that reference at least one of the list items in and out or an in-out clause. And then out or in-out are actually synonymous in their meaning. It means that the generated task will be a dependent task of all previously generated sibling tasks that reference at least one of those list items in any depend clause, okay, regardless of what the type is. So that looks a bit, that's kind of the formal statement, which is slightly convoluted, but essentially it allows you to do things like this. Okay? It says, okay, if I have 3 tasks and yeah, hi Juan, yeah, I'd turn my camera off to try and improve the quality of the audio. Let's try that. Okay, yeah. So suppose I have three tasks here, and I want the third task only to execute when the first 2 have completed. So this is a simple example where it's possible to use a task wait, for example, but it's easy to think of much more complicated dependency patterns which are difficult or in fact impossible to code correctly with task waits. So if I specify basically an out dependency on A for the first one and an out dependency on B for the second one, and then an independency on both A and B for the third task, that means that the first 2 tasks are able to execute in parallel, but the third task can't complete until the first two are complete. The third task can't start, sorry, until the first 2 are complete. So it's possible to code quite complicated dependency patterns with this, and actually there is no real, although you probably expect the use case to be that that first task actually wrote A, and the second task wrote B, and the third task read A and B. That's not a constraint actually. So there's no real connection between the items that you put in and how they're used inside the tasks. And sometimes it's actually more convenient just to create some completely fake variables that you never use for any values, but you just use them to express the task dependencies. Okay, so last one is thread affinity. So OpenMP4 gives you a lot more control over thread affinity. So, and the motivation this is because we've got a lot of NUMA systems and also SMT, simultaneous multi-threading hardware threads available. So it means that the placement of the threads on the hardware can have a significant effect on performance in some cases, particularly when you're using nested parallelism. And so if we just have one level of parallelism, then it often doesn't matter too much which thread gets bound to which core. But once we start having nested parallelism, then it starts to be more important. So the way this is done is as additional choices for the OMP proc bind environment variable. So you can still specify just true or false, but you can also provide a list, and the values that can take are master, close, and spread. And that specifies how to bind the parallel regions at different levels. And there's also an OMP places environment variable. So that basically allows you to specify the hardware entities that you want the binding to happen to. So typically you can specify abstract names such as threads, which means hardware threads in this case, cores or sockets, and you can also specify an explicit ordered list of places. So you can do things like you can specify a particular set of cores that you want your threads to be bound to. The way the places are numbered, so the way cores are numbered, cores or hyperthreads or whatever are numbered is implementation defined. So you have to go and look up the compiler documentation to figure out how that's done. Okay, so it's maybe a bit easier to understand with an example. So what you can suppose I have 2 levels of nested parallel regions, and the hardware has 8 cores in it, and each core has 4 hardware threads. So I can say, okay, I want nested parallelism. So I can set my OMP num threads variable to 4,2, which says give me 4 threads at the outer level and 2 threads for each of the inner parallel regions. And then I can say, okay, then OMP places equals threads. So that means I'm talking about threads as the binding entity here, and the binding rule is spread and then close. So what that will do is that essentially the original master thread will get bound to most likely hardware thread 0 on core 0, and then the first level of 4 threads in the top level, in the outer level of outer parallel region, those will get spread out as far as possible. So those will get spread out as much as possible. And then if I say close for the inner one, so what that actually means is that it'll keep those within the range, within the split of the outer one, and then start scheduling them cyclically. Okay, so I'll actually, in this case, it'll actually end up with, so I've got 4 threads for each of these inner parallel regions, and what I will end up with is 2 on each of these pairs of cores. Yeah. If I said master here, then I would end up with all 4 threads on the same core. So it's a bit complicated to get your head around how this works, but you can see that it in principle gives you a lot of control about how threads get bound to your hardware entities. Okay, so any questions about that stuff? Gianpaolo, yeah.
Hello, can you hear me?
Yes.
Okay. Yeah, about the binding. I don't know if I missed it, but if you don't specify, the binding, I mean, is there a default or? I mean, what would happen, when the nested parallelism?
If you don't say anything, then you probably don't get any thread binding. Okay, so I think you probably get, it's probably the same as saying OMP proc bind equals false.
But does it mean that every time the nested parallelism is called in my use, every time different course as well? Or does it remember on which course did it run?
No. If you don't specify binding, then you're essentially at the mercy of whatever the operating system wants to do.
I see. So, I mean, do you recommend?
So, I mean, you know, if you haven't oversubscribed the system and you know there's nothing else, there's no other busy processes or threads running on your hardware, then most likely the threads will end up somewhere and mostly stay there.
Okay.
But you're then just relying on the operating system's scheduling policy to handle it how it feels like.
Okay.
But if the operating system feels like it, it's perfectly at liberty to move your threads around.
I see. Okay.
So you have to. In reality, OpenMP implementations don't actually create new threads for every parallel region. Okay. They don't create new. Don't create brand new operating system level threads every time. They typically create a bunch of threads at the start of the program, and they will keep reusing those operating system threads will be kept alive and reused for every parallel region.
I see. Okay, thank you very much.
Okay, so so as long as the underlying operating system thread doesn't migrate, then you'll get this. Every parallel region will essentially have the same mapping of threads to hardware, but there's nothing to really guarantee that. Okay,
so it generally is, if possible, it's better to specify the binding.
Yes, so if you just have one level of parallelism, then probably just specifying OMP proc bind equals true is enough.
Okay.
Just to say, I don't mind where the threads go, but just don't move them while they're, once you've put them somewhere, don't move them.
Okay, perfect. Okay, thank you.
Okay, another. Can the placement and can you also change stuff within the code? That's a good question. You need to look up how much control you really have once you're inside the code. The answer is basically no. You can query it, and there's quite a lot of facilities to ask what your binding is, but essentially there's no way you can change it once the code starts executing. Okay, so final talk is about the accelerator offloading capabilities in OpenMP. So the accelerator support in OpenMP is essentially designed to be not GPU specific. It's designed to work well or work reasonably well with GPUs, but it's designed to cope with other devices. Not that there are very many other interesting devices around at the moment. Yeah, it is basically all about GPUs. While this specification was originally being designed, then the sort of Intel Xeon Phi, the first generation of Xeon Phis were around, so it was kind of also designed to work sensibly with Xeon Phis in offload mode. But then the next generation of Xeon Phis went to kind of, you know, not being a CPU rather than an accelerated device, and then of course they've now disappeared, and Intel are now going to produce GPUs. So you know you'll still be able to use this, but it's for Intel devices, but they're now essentially going to be GPUs as well. So it's kind of fully integrated into OpenMP for the CPU, in the sense that it's, you know, it's well defined how the offloading to devices interacts with the threaded parallelism on the CPU. So it first came in 4.0, so it's been around for a while, but there were some significant revisions and extensions in 4.5 and 5.0. So it's similar to, but not the same as, another specification called OpenACC, which you might have come across. Okay, so OpenACC is an alternative standard for offloading to GPUs. It was developed before OpenMP 4.0. It's still around. The functionality of the two standards is essentially equivalent. Anything you can do in OpenACC, you can pretty much do in OpenMP, say 5.0, and vice versa. But all the syntax is different. And OpenACC is really focused on GPUs only, so it has some of the sort of semantics in OpenACC are really very or a bit more tightly coupled to GPU hardware than the OpenMP stuff is. So there are. So what is there out there in usable OpenMP implementations for GPUs? So Cray compiler, IBM, LLVM, Clang, GCC, and recently also, thankfully, the NVIDIA compilers now also support OpenMP directives for offload to NVIDIA devices, which has been a long time coming, and I think there was a fair bit of resistance early on in NVIDIA to implementing it, but they've gone and done it now, which is actually nice, because installing anything else is, you know, it's like things like GCC and Clang. Installing versions of those compilers that actually work with GPUs is a complete pain. So having OpenMP capability bundled along inside the NVIDIA compilers is a significant step forward in just making it easier, making this easier to use. Okay. So what's OpenMP's view of abstract view of the hardware like? So that's basically its device model. So this is essentially a host-centric model. So it assumes you have one host device, in other words, your CPU, and then multiple target devices of the same type. So it assumes that you have, say, a number of GPUs on your node, but you don't have, OpenMP doesn't cope with sort of heterogeneous systems where you have different types of devices. Okay, so a device is formally, so it's a logical execution engine with some local storage, and then the OpenMP specification also talks about a device data environment. So that's basically a data environment that's associated with a target data or target region construct, which we'll see how that works. So essentially, kind of, it assumes that there are essentially separate copies of variables which can exist on the device. So they share the same name as variables on the host, but there are basically mirrored copies of data structures on the device. There are a set of target constructs, and these control how both the data and code is offloaded onto the device. Yeah, we have this notion of data being mapped from the host data environment to the device data environment, where the variables have share the same name, but they're actually mirrored copies of each other. Okay, so in this sort of similar vein as the way the parallel region is the basic multi-threading construct in OpenMP, then the target region is the basic offloading construct. So it works in a similar kind of way. The target region defines a section of a program. The OpenMP program starts executing on the host, and then when a target region is encountered, the code contained in that target region is executed on a device. And if we don't specify anything else, by default, the code inside the target region executes sequentially, which in most cases is probably useless. So if we want to have parallelism inside the target region, then we have to ask for that explicitly. At the end of the target region, the host thread waits for the target region code to finish and then continues executing the next statement. So the host and the device synchronize at the end of the target region by default. You can remove that synchronization if you wish, but it's there by default. So it just looks like, the basic form just looks like hash pragma OMP target with a structured block of code. Okay. And so this works pretty much how you expect. You start off executing in the sequential part of the program. You start off executing with the master thread on the host device. Then when we reach a target region, the body of the target region is then offloaded onto this executes on the device. And then at the end of the target region, the original thread on the host waits until the target region is complete. It then carries executing again, and then we can have as many target regions as we like during the lifetime of the OpenMP program. So most of the complexity comes from dealing with the data. So we have both host and device data. So the host and device have separate memory spaces. And in order to access data inside the target region, it has to have been mapped to the device first of all. And then because now we've got multiple copies, the rule is that the map data mustn't be accessed by the host until the target region has completed. So if we remove the blocking constraint from the target region, it would then be possible to have it'd be possible to write code where you had both the host and the device modifying the data at the same time, but you're not allowed to do that. Okay, so because there's no way to make those two copies consistent again at the end of the target region. So there's some default behavior, at least from 4.5 onwards. So just to save you some bother here and a bunch of typing. So any scalars that are referenced in the target construct are treated as first private. So essentially you get a new copy on the device which is initialized with the value that it had on the host. So for scalars you automatically get an initialized copy on the device. And then by default also static arrays are copied on entry and copied back to the host on exit. But you can override all this behavior. So the way you get full control is through the map clause on the target directive. So you can have different options here. You can have map2, which copies the data to the device on entry to the region. You can have map_from, which copies the data back from the device to the host on exit. You can have to_from, which does both of the above. And then you can also have an alloc map type, which basically says, okay, I don't want to do any copying here. I just want to allocate an uninitialized copy of this data structure on the device at the start of the region, but don't copy any values. Okay, so a simple example. So suppose I had a loop like this that forms the sum of that basically does dot product of two vectors. Then I can offload this onto the device with this construct. So OMP target, and then I need to map the vectors from the host to the device. So I say map2 for B and C, and then for sum, I both want to transfer the initial value of sum to the device and the final value of sum back from the device again. So I can say map2from for sum. Okay, but as far as this goes, this loop will execute sequentially on the device. So at this point, this isn't much use for anything. If we've got dynamically allocated data, then at least in C and C++, we need to specify the number of elements to be copied. Okay, so suppose B is actually a pointer to which I've mallocked some amount of storage. Then if I want to map that storage onto the device, I have to use this square bracket syntax here. So to tell the compiler where to start. So the first element here is the starting element of the array, and the second parameter here is the number of elements. So the number of words, not the number of bytes. You can use this to specify a subsection of an array if you want to here. But just to note that the syntax is basically start:\length in C++. So that's not the same as the Fortran subarray syntax, which is start:\end. And this syntax is also useful in other contexts in OpenMP. You can use it in reduction clauses to specify point-wise reductions on arrays. Okay, so far so good, but There's a problem with a lot of current hardware, particularly GPUs, in that moving data between the host and the device is basically slow and expensive. So in order to get reasonable efficiency, we'd like to avoid mapping data in every target region. If it's possible to keep it on the device, we'd rather keep it on the device between target regions rather than keep moving it back and forth. So there's a couple of extra constructs that allow us to do this. So the target data construct, this just maps the data and doesn't actually offload any code. And then there's also an update construct, which at any point you can copy values between host and device in either direction. So the data constructs look like this. You can say, suppose I have a target region which is going to be executed lots and lots of times, and every region is going to access these arrays A and B. But I'm not interested. In between time, I'm not interested in knowing the values of, or having access to the values of A and B on the host. So I can enclose all this offloading of code inside a target data region. So at the beginning, I can say #OMP target enter data, and then do the map of these arrays to the device, and then do lots and lots of target offloading, which use A and B, and then maybe at the very end, perhaps I'm only interested in getting B back. I could say exit data map from B, and that'll bring the values of B back onto the copy the values of B back onto the host at that point. And then also, for example, I can do data copies at any point between target regions. So again, suppose I had this data region. So I did the same thing here. I got map to A and B. Then I have a target region which does something with A and B, and then essentially I want to get one. Maybe I'm interested in getting one element of A back onto the host to do, and it's going to modify it in some way, and then I can use so I could use update from to get the value, to get A0 from the device, do something with it. Push the new value of A0 back to the device, and then carry on doing stuff with A and B. So I'm basically being very specific about exactly when and exactly which elements of the array are being moved around. So you can really minimize the amount of data that's being shuffled around. Okay, so that's really how data is handled. Now we have to think about parallelism on the device. So in principle, we can use all the normal OpenMP constructs inside a target region to create and use threads on the device. So parallel regions, work sharing, all the synchronization contracts, tasks, etc., etc. However, GPUs can't really support this. They're not able to support a full threading model outside of a single stream multiprocessor. And so most GPUs have this architecture where you have multiples of these stream multiprocessors on the GPU, and then each stream multiprocessor essentially runs a bunch of threads in a sort of Cindy-like fashion, really, so semi-synchronized fashion inside the stream multiprocessor. So why not? Okay, well, it's really because there's the GPU hardware doesn't support synchronization or memory fences between the SMs. There isn't any coherency between the level 1 caches. So each SM typically has a level 1 cache, but there's no coherency. What happens is a parallel region inside a target region will only use one of the SMs. So inside an SM, you have all this synchronization facility available, so you can execute a parallel region inside an SM. But really, that's still not much use. Okay. So I mean, this, if you're familiar with CUDA, then you see the same kind of the same corresponding restrictions in CUDA. You can only synchronize threads inside a thread block and not between thread blocks. So we can extend the example with some parallelism by just doing the conventional thing with this loop, which would be a parallel for with a reduction for some. So on other devices, if they existed, that might work fine. But on a GPU, that's only going to utilize one of the SMs, so it's still not much help. So the additional thing in OpenMP that allows us to use the whole of the GPU is the teams construct. So what this does is it effectively creates multiple master threads inside a target region. So instead of your target region starting execution on a single thread, it's possible to create multiple master threads inside a target region. And then each of those master threads can in turn spawn its own team of threads with a parallel region. But there are the sort of restrictions that mirror what the hardware is capable of here. So threads in different teams can't synchronize with each other. So the synchronization constructs like barriers, critical regions, locks, atomics only apply to the threads within a team. And then you have some control. You can set the number of teams and query the current team ID and the number of teams and all that kind of stuff. So we end up with this hierarchical parallelism on the device that essentially is designed to match GPU hardware. So when we reach the target region, then we can also have so typically what we'd have is a target construct, which contains a team construct, which also contains a parallel construct. So the target offloads onto the device. The teams construct creates a collection of master threads, and then each of those master threads in turn creates a team of threads with the parallel region. So each team creates a separate parallel region. So, and then it's not possible to sync. Once we're inside this parallel region, we can only synchronize with the other threads inside this parallel region and not across different parallel regions. And then we also have kind of the team's equivalent of a work sharing construct. So because loops are the most common source of parallelism, and particularly so for GPUs, then if we offload a parallel loop to the device, we'd like to be able to distribute the iterations of that loop across the teams as well as across the threads within the teams. And so there's a distribute construct to do this. So this works just like the for construct, but it assigns iterations of the following loop to different teams rather than to different threads. And there's a schedule clause here, but we, again, because of the restriction of being able to synchronize between teams, we can only have static schedules. So we can have static or static with a chunk size, but we can't have things like dynamic or guided schedules. So if I really want to do something useful with the example that I started with, then I actually need this horrible long directive. So there's a bunch of combined forms here, so you don't have a whole big stack of directives. But what I would need to do is have hash pragma OMP target teams distribute parallel for. So that basically says offload the code to the device, create a bunch of teams, distribute the loop iterations between the teams. Each team creates a parallel region, a set of threads, and then also distribute the loop iterations across those threads as well. Okay, so this will distribute the loop iterations both across the streaming multiprocessors on the GPU and across the multiple threads between each multiprocessor. Okay. So another piece of convenience is that if you want to call functions inside target regions, then you need some way of telling the compiler to compile that function for the device as well as the host. Okay, and basically you can do that with a declare target. So if we include the prototype for the function inside the declare target directives, then that means that tells the compiler that it needs to compile this function for execution on the device. And then if we do that, we can call that function on the inside a target region. Other things you can do, so if you have multiple devices, so if you have a node with multiple GPUs, then the target directive takes a device clause which allows you to specify which device to offload to if there's more than one. And as I said before, the host thread will by default block until the target region is completed. You can add a no wait clause to prevent that happening. The target region then actually becomes a task as far as the host is concerned. So task synchronization constructs like task wait can be used to wait for completion of these of target regions with no wait clauses. But as I kind of mentioned before, then it's up to us as programmers to make sure that the host doesn't access any of the map data before the target region completes. And then, as ever, it's as with normal OpenMP, it's fairly easy to get stuff running, but it's more difficult to get stuff running efficiently. So there's obviously some additional performance considerations. First one I've already mentioned: transferring data between the host and device is liable to be expensive, so you need to minimize as that much as possible. So don't transfer anything that's not needed, and keep the device on the data as far as possible with target data regions. GPUs typically need a lot of threads to work efficiently, and so whereas your CPU might be talking about order tens of threads at most, then GPUs might be talking thousands of threads to make them work efficiently. So that means that we need to expose a lot of parallelism, so much more than for the CPU. So that means that it's often more important to extract all the parallelism from nested loops. So using the collapse clause here is typically a lot more useful for GPU code. So it allows us to parallelize multiple loops in the loop nest to get enough loop iterations to keep thousands of threads busy. Then we also have to worry about things like memory layout on GPUs, because this is it works the opposite way around to what you're used to for CPUs. So for CPUs, if we have different threads accessing neighboring words in memory, that can be bad because we have this risk of false sharing. Obviously, it's okay if it's just reads, but if if at least one thread is writing, then this is bad for performance on a CPU. Or conversely, for GPUs, having different threads accessing neighboring words in memory is actually good, because it allows the GPU to generate these coalesced load and store instructions. So that means if your data structures are being used on both the CPU and the GPU, it might be necessary to explicitly change the layout. So for example, you might need to explicitly transpose multi-dimensional arrays before mapping them onto the GPU. You might also get away with other things. You might be able to interchange loops and or use a static one schedule to get the right interleaving behavior on the GPU. Okay, anybody, any questions? Nope. Okay, so I'm sorry that we can't play with this. So with multiple GPU systems, we need to use target region multiple times with different device values. Yes, you do. Okay, so there isn't a kind of automatic way to split target regions across multiple devices. But you could, for example, you could create multiple threads on the CPU and have a so if you had 4 GPUs, you could create a parallel region with 4 threads on the CPU and then have each different thread offload to a different GPU. Well, that's the end of the lecture material for this course, and I obviously appreciate it's a Friday afternoon, and that some of you are an hour ahead of the UK time anyway. So please, if you've had enough and with the practical sessions for today, then please don't feel obliged to hang around. But if you do want to, then I'll be around. I'll be around until 5 o'clock UK time. If anybody has any more questions or queries, I'll take a short break now and then come back. Just a couple of final reminders. Remember that your temporary accounts on ARCHER2 will disappear in a couple of weeks' time. So please make sure that if you want to copy anything that you've done off ARCHER2, that you do it before that happens. And lastly, be great if you could fill in the feedback form. So if you can do that by going to the page for the course on the ARCHER2 website. But Claire will also send you an email reminder as well. And it would be very helpful to get your feedback, see what you thought of this course. It's the first time I've run it in like this 2-day format, so I'd be very interested to hear what you thought of it. Otherwise, thank you very much, everybody, for taking part. It's always good to hopefully tell you some useful and interesting things. I hope it has been. I hope it's, at least some of it's been useful for you. And thank you for your participation.